So electron 2 is basically extrinsic semiconductors. These are doped, they're impure. They contain an element other than silicon. Now this one, the first picture you're looking at, has boron. Boron is from group 3, so it has one less electron in its outer shell. That's obviously, I've coloured it yellow in case you're wondering which one it is. It only has 3 electrons in its outer shell, which means there's a space, a hole, a space where one of the other electrons, which heat or some other form of energy releases from other parts of silicon, can be filled. It can jump into that space. And that's why this is called a p-type, because it appears that the holes, the spaces, are moving, that they are going from one place to another, like an empty chair in a doctor's. Like as one person gets up, the empty chair moves from left to right. So let's look at boron. There is its 3 electrons in the outer shell. It's got 5 protons, but there's only the 3 in the outer shell we need to worry about. If we have a silicon crystal and we take away one of the silicons and replace it with a boron, what you have created is an extra space. So you have 3 covalent bonds, as you can see, but 1 free electron. But that also creates a space where another electron can jump into, and that's called a hole. So you have a hole which can be used as conduction. Now really electrons are moving, as they always are, but we consider this hole positive. So this is a p-type semiconductor. Now, if we change that, instead of adding boron, we add arsenic. That has 5 electrons in its outer shell. We get an extra electron. An extra electron which is not bound in one of the 4 bonds. If it's not bound in one of the 4 bonds, it's available for conduction. There's negative conduction, n-type. So here's the phosphorus. That's it there. We've got the silicon again. We take out the central silicon and we add a phosphorus atom into the middle. And if we do that, then what you can see is we get an extra electron. There we are. Extra electron, free to conduct electricity. So that electron is now not bound. So if we look at extrinsic semiconductors, and this is a p-type with extra holes, it seems that the holes are moving, but really what's happening is electrons are jumping to fill the holes. And of course, holes being positive in a p-type, they'll be attracted towards the negative pole. So this is a p-type semiconductor. So now we have 2 types. We have this type with P, which is, as you can see, doped with boron, and another type which is N, which we dope with silicon. Now the 3 scientists who were first working on this, Shockley, Bardeen and Brittain, weren't getting on very well, so they ended up making a mistake, growing 2 crystals, one half of which was P and one which was N, and they couldn't work out why it would conduct electricity sometimes and not others. And Shockley, who was easily the nastiest of all of them, actually worked out that it was because they were the same crystal, that he'd actually created a valve. You see, because close to where the P and the N type meet, there's too many electrons on one side and too many holes on the other. So some of the electrons naturally jump over and fill those holes. This leaking of electrons from one type into the next across the barrier is probably why we have modern society. It's the creation of this thing, which is essentially a switch which will work at light speed, which is the junction diode. Before this we had valves, enormous things that look like light bulbs that were really almost virtually useless. But because of this combination of electrons and holes at the junction between a P and an N, you create a large area where there isn't anything. There's nothing to carry the charge. That area is called the depletion zone. There it is. And what's happening here, the electrons and the holes are combining and leaving absolutely nothing to carry the charge. So when that depletion layer is in place, there is no way of conducting electricity. It acts as an insulator. However, it's not impossible to get rid of that barrier. You simply put a forward bias on it. You connect the P to the positive, the N to the negative, then the depletion layer disappears and it conducts electricity like it was a wire. This is great. You've turned it on. It's a switch which is now in the on position. Switches usually take a considerable amount of time to turn off and on, but not the junction diode. by simply switching the polarity by connecting the positive to the negative side and the N-type to the positive side, the depletion layer much grows. This is called reverse bias. In reverse bias, the diode doesn't conduct electricity. So forward bias, reverse bias, forward bias, reverse bias, these are the ones and zeros. This is digital code. On or conducting is 1 and off or not conducting is 0. As everything in life is now ones and zeros, it's all basically diodes. Okay, just a word about the junction voltage. Now, in the depletion layer, there's a small voltage of 0.6 of a volt that has to be overcome before the thing conducts electricity. So in its natural state, without being laced up to anything, there's a 0.6 volt depletion layer. However, if you connect it in reverse bias, so that the positive is connected to the negative pole of the battery, then what essentially is happening is you're drawing the positives towards the negatives and increasing the size of the depletion layer. The depletion layer grows. That's a 0. If you turn the battery around the other way into forward bias, the electrons are repelled by the negative side of the battery and attracted by the positive side, and the holes are repelled by the positive side and attracted by the negative side, and the depletion layer disappears, and you get a certain amount of conduction. Now, it's not as good as a wire, it's a semiconductor. It's about halfway between the conduction of a conductor and an insulator. That's what a semiconductor is, halfway between the two of them. But you do get conduction, and that's where you get your ones. Now, I've already mentioned how this is basically a switch which is used in computers. But the most important fact about the diode is it only allows electricity to flow in one direction, which is why we have the symbol for it. The arrow is the direction that conventional current will flow in, whereas it won't flow in the other way. So if you take a diode, the one on the left is connected correctly and light, the one on the right doesn't. The one on the left, you get a flow of current around because it can go through the diode. The other side acts as a barrier, so you have forward bias on the left and reverse bias on the right and no conduction. You don't even need a bulb because you have a light emitting diode so that they'll light up in forward bias and not light up in reverse bias. They're like your pin lights on all sorts of manner of equipment. So this is a very important thing. This is the characteristic curve. This is the relationship between current and voltage. And as you can see, it doesn't start at 0, 0, and it isn't a straight line. So you can't say this follows Ohm's law. What you have there is the 0.6 of a volt it needs before it overcomes and starts conducting. And that's called the junction voltage. You can also see there, I'm flashing it, that the curve looks very different in reverse bias, that it's much flatter, showing there's almost no conduction in reverse bias. And that characteristic curve shows just about everything you need to know. It shows that there is conduction in forward bias, though not ohmic, and that there is very little or no conduction in reverse bias. It also shows that it takes 0.6 of a volt before conduction starts at all, and this is called the junction voltage. Now, to investigate the diode, we need two different circuits. This is the forward bias circuit with a milliammeter and a voltmeter. The variation in voltage and current is done by sliding the slider on the rheostat, shown as a variable resistor. Also notice I haven't put in a battery, but 6 volts positive and negative. The idea of this is that you can't get the battery around the wrong way, really. Now, when you change over to reverse bias, you put the battery or the diode around the other way. Here I've reversed the diode. Now, all is the same except we've moved, if you notice, the ammeter from outside to inside where the voltmeter is, because the current is so small it wouldn't detect it. It would be skewed by what's going through the voltmeter. It's also a microammeter, much more sensitive. So you can plot that characteristic curve using these two circuit diagrams for forward and reverse bias, and they need to be remembered. They are very important. So what can we use it for? Well, the main thing we're going to use this for is as a rectifier, to take main signal and to turn it into, well, in this case, half wave rectification, as you can see here. The whole wave, or the mains output, is shown as travelling in two different directions. The upper part of the wave is travelling in the conventional way, and the lower part of the wave travels in the opposite direction. Now, what half-range rectification does is simply chop this in half. It takes the top half of the wave only when it's travelling in the right direction and rejects the lower half, and we get that bumpy wave, which is of course useless to us. So what we need to get is smoothing. Smoothing is adding a capacitor so that when we pass the mains through a half-wave rectifier, instead of a very bumpy wave, we get a slightly less bumpy wave. Now obviously a better capacitor will give you a perfectly smooth DC wave, which is what we're aiming for. Basically turning the AC wave into a DC wave, again, just by having a good capacitor. Here's the first amplifier. That's under a glass jar somewhere. William Shockley, just thought I'd put that in case you could see it, if you can barely see it through the glass. Bell Labs, MIT, great place. Lots of inventions happen there. It's all moved west now, largely because Shockley moved west. It's a long story, I'll tell you it some other time. Anyway, here we have the question I've set you. Hope it's easy enough. It's just half a question, 12 if you remember. There's 4 parts and you only have to do 2 of them. This is question 12B. It's a nice little question. I think it'll be good for you for revision. Okay, next we're going to do the photoelectric effect.